Yes, hello. This is just a tutorial on another leet code problem. So this one is medium difficulty, and what we are asked to do here is essentially to remove a cycle from a tree. So in these graphs, there's a cycle, and we want to remove that cycle and preserve all the other, or all the nodes really, just remove the cycle. So there's one edge causing a cycle and we want to get rid of it. You can feel free to pause and read the problem, which is essentially what it asks us to do. It gives us a vector called edges, and all of the edges are represented by a two-dimensional vector. So edge 1 and 2 is this line here in between the nodes 1 and 2. So this is the edge, and so on for 1 and 3, 2 and 3, etc. It's for 1 and 2 up here. And then for down here, it represents this picture here. So I'll zoom in a little bit for clarity. So this set of edges represents this graph. And what we want to do is find which one of these edges or which one of these lines is causing a cycle in the graph. A cycle that's basically just when you can reach the same node by traversing it. We're supposed to have a tree-like structure here, but obviously it's not a tree because there's a cycle, and trees cannot have cycles. So I think it would be helpful if I draw it out. So, okay, uh, that's not it. I'm gonna start another note here. And what we're gonna do, we're gonna just explain how we're gonna solve this problem. So basically, we have a series of edges. So we have, for example, like edge 1, 2, and this connects node 1 and node 2. Notice that they're all in sequence because that's what the problem says. The problem says you start and you go up in sequence and they're in order from 1 to n, where n is any number, any positive number. There is some constraints to that based on the problem, but that's essentially it. And then, say for example, you have 3 and then 4. So what we're going to do to solve this, we are going to use something called DSU. That's this joint set union. Okay, set union. So what that's going to do, it's going to create groups of each of the node, and each group is going to have a representative. So now we're grouping them. So we have 4 groups: group 1, group 2, group 3, group 4. And let's say, for example, we join these 2 groups. Now we have group 1 and group 2 grouped together, and then you have 3 and 4. So now you basically have more space to understand that one of these is going to have a representative. So out of this group, let's say 1 is the representative, and out of this group, 3 is a representative, and out of this group, well, 4 is a representative because those are the only ones that can be. You can represent this by 1, or you can represent this by 2. It doesn't matter as long as we represent it correctly. We should be able to solve that problem. And we're going to keep joining groups until we see that 2 groups share the same representative. So if, let's say, for example, node 3 was in here, so we have 1, 2, 3, and our representative is 3, our representative is 3 and 4, then this is an issue. This is not good. This is the edge causing the problem essentially. And I'll explain that much more in depth here soon. But we're going to start by just programming the solution into the actual vector. So we're going to create a int n, which is going to be the size, and then a vector of integers. So I did do n plus 1, so it's size plus 1. And I did size plus 1 because I'm going to add one more item to the list that we're given, and that's just going to be 0 for convenience sake. That way I don't have to worry about indexing, which can look confusing, especially for a tutorial video. So we're going to abstract that away. So I'll explain what that is. So continuing with the previous example, we had 1, 2, 3, 4, and that is all of the possible nodes. But what I'm doing is I'm doing 1, 2, 3, 4. I added an extra element. We're just going to ignore this. We're never going to use it, but I did add it. The reason I added it is to simplify the understanding of what's going on in the code. And what we're going to do next is essentially pre-fill the array using iota. So say p.begin, and then p.end. So these are just iterators, not indexes. These are iterators that we are using to pre-fill the vector from which we have already specified the size of. So we are pre-filling. Essentially what this does, completely independent of the vector, what this does here, it essentially, essentially it will do this. It will take any vector of the size that you give it. So let's say the size is 2. So remember we did size plus 1. So that's 3. So what it's going to do, it's 0, 1, 2. The size is 2, but then we added the extra item. See? Hopefully that makes sense to you. So now we're going to go ahead and do a little lambda function here. And we're going to make sure to pass the value by reference so we can modify that value. And we're just going to call that value x, and we're going to define that here. And we are going to say p. So p stands for parent. That's why I called my vector p. P of the integer that we're passing in as reference. So px is not equal to x. So when they're not equal to each other, well, first of all, when they are equal to each other, we're going to return x. Just going to return itself when it's equal to itself. And it will not equal to itself many times. It sounds dumb to say when something is not equal to itself, then perform the function, but you'll see why that works here in a moment. Say p, and we're actually going to access the item inside of itself. So say p of x, the subscript x. So whatever item is inside x is what we want to access. So that's why we do p and then nest it inside p of x. And this is very simple. So we'll move on to the next step. All right, so I'm just gonna actually add a comment here just for explanation. All right, so we are gonna go on to the next for loop. We're gonna say auto, and we're gonna pass this by reference, and we're gonna iterate through edges, and we're gonna make some changes here. So we're gonna say int a find, and then x of 0, and then b find x of 1. I'll explain why I'm doing this here in just a moment. A is equal to b. Then if they are, then just return the actual node that we found. So x represents a node. A node is represented by an edge, and this is a vector of edges. So we're actually returning the edge, which represents the two nodes, I should say, the connection of two nodes. Should be more clear with that. All right, so now, okay, so yeah, we are going to go ahead and set P of A to B to represent that we've already visited that edge. Okay, so that's going to set the representative. So the actual B node will be represented by a representative at subscript A. Great. And I'll just add another comment here for convenience. Yin yin. And then turn first cycle edge. And we can go ahead and try that. It looks like I have an error. Oh, well, if we don't find it, we're just going to return this, return emptiness. So this should never execute, but it is required. And yeah, as expected, it works. We're going to submit against more tests. All right, so great, it worked. This is not my account, by the way, this is my friend's account. But now we are going to explain why this works. So let's walk through, this one's easy. We'll walk through this one, it's a little bit more challenging. So I'm going to go ahead and copy paste this, which represents this graph here. Well, it looks like that didn't work as expected. All right. So the first edge is 1, 2. Okay. So we're going to say A is equal to 1, B is equal to 2. Now, if you remember in our for loop, you can go back and check. We say call the find function on x of 0 and call find on x of 1 as well. So this represents A, this represents B. So really we're calling find on A and we're calling find on B. So this is our A, this is our B. So let's do the logic that's inside the find definition. So just as a refresher, find is over here. And remember, we're passing it by value because we are going to modify its value. All right. So the logic says while P at X is not equal to X. In this case, they are equal to each other. So we're just going to return X. So 1 is equal to 1 and P subscript 1 is equal to 1 as well. And B subscript 2 is equal to 2. And B subscript 2 is equal to 2 as well. So for both of them, we're just returning themselves. Because right now, if you remember what I said up there, you have P and then 0, 1, 2, 3, 4. And that should be all the edges that we have. For this one, actually, it has a fifth. So there's 6 items in here, but we're only working with 5. Okay, so as you can see, subscript 1, subscript 2, we're just returning each other. So what happens once we return? When we return, we go ahead and come here. Okay, so when we return, we go back in here and we do this check. If A is equal to B, so is 1 equal to 2? The answer is no, they are not. So since they are not equal, we're gonna skip this part and we're gonna go right into here. So what does this say? It says P of A is equal to B. So what is P of A? A is 1, as you can see here, and P is all the parent vector that I created. So P of 1 is equal to what? To 1 as well. Okay. So we're saying at that index, at that item, we need to go ahead and set it equal to B. And if you remember, B is equal to 2. So then we're quite literally saying remove the item that's in there and place B, copy it into its place. So we're going to say, we're going to go ahead and say B is now equal to this. I don't actually have to rewrite that. So this changes now. So now we have P is equal to 0, 2, 2, 3, 4, 5. So now 1 is gone, but it's being represented by 2. So 2 is a representative of that group. So in here, there's a group, and the group is 1 and 2, but we're compressing it and only displaying the representative, which is 2. Okay, so now on to our next set of 2 actual nodes. So it's now we have 2 and 3. So this time 2 is equal to A and 3 is equal to B. Okay, so we are gonna do the same thing. So remember, we're checking the while loop condition. So that condition says P of X, we're checking if that is equal to or not to X. So first, we're going to use A for X. So we're really saying, while P of X, so P of 2, just 2, is this not equal to the actual value, which is 2? So are they not equal? No, they are definitely equal. So we are going to go ahead and move on to the next step. So we do is return 2. So that's it. We're not going to actually execute any logic there. And then for the next one, same thing. So you can just replace it with the x is 3 subscript 3. So it's 0, 1, 2, 3. This is subscript 3. Is 3 not equal to 3? Well, yes, they are equal to each other. So we're also going to return 3. So I'm just going to represent that by saying R3. So return return 3 as well. And we're going to go ahead and check is 2 equal to 3? No, they're not. So we skip the next check and we go back to P of A is equal to B. So P of 2 is now equal to 3. So now we have P is equal to 0, 2, 3, 3, 4, 5. So now 2 is being represented by 3. Or 2 and 3 are being represented by 3. Their connection at least. So before we had 0, 2, 2, 3, 4. The only thing that should have changed is this one. So let's double check that. 0, 2, and then 3, 4, 5 afterwards. 3, 4, 5. And that is in fact the only one that changed. Okay, we're done with our second check. Now let's move on to our third one, which is 3 and 4. So A is equal to 3, B is equal to 4. And just keep in mind that we haven't actually executed this yet. We have not executed this yet. We've been skipping this so far because this condition has never been met. Okay, so now we go in here and we're going to say, while, again, subscript 3 is 0, 1, 2, 3, while 3 is not equal to 3. So they're just going to return 3. So, and next, I'm going to say, well, okay, while 4 is not equal to 4, same thing, return 4. And then we're going to say P at 3 is equal to 4. So now we have P 0, should be 2, 3, and then 4, 4, 5. The only one that should have changed is this one, 0, 2, 3, 4, 4, 5. Okay, great. So that's it. On to the next one. So the next one, we just did 3 and 4, I believe. Yeah, 3 and 4. So now we're going to do 1 and 4. All right, let's separate this. So A is 1, B is 4. I just want to emphasize that we still have not executed this line yet. And that line is very key to how we're going to find the solution. Okay, so we're going to go ahead and check while subscript 1, remember? So while 1 is not equal to 2, then we're going to go ahead and execute. Actually, I wrote that backwards. While 2 is not equal to 1, then we're going to say 1 is equal to P of X, and that is going to be equal to P of P X. Okay, so let me just help you walk through this. So 1, and then P of X. So we have 1, P of 2, which is 2. So P of X is 2. And then we're going to say P of X, which we know this. What is this? Remember, we just did it. It's 2. It's right here. So P of 2. So what is P of 2? It's 3. It's 3. So we're going to say P of X, or more specifically, P of 2 is now equal to 3. And we're also replacing X. So P of 2 is now equal to 3, essentially. I'm sorry, P of 1. I miswrote that there. P of 1 is now equal to 3. All right. So now we are left with P 0, 3, 3, and then 4, 4, 5. 4, 4, 5. Okay, very good. So now we can move on to the next iteration. So 3 is still not equal to 1. So we're going to go ahead and do the while loop again. While now P of 3 so P subscript X, and X is now 3, is not equal to 3, because remember X is now 3. So they are equal to each other because, actually no, because 4 is at 3. So we're going to say index 4 there is the same as 3. So we have 0, 1, 2, 3. So I guess just for clarity, we can say this is 4 because it's right here. So we're going to say 3 is equal to P of X, which is equal to P of X. 3 is equal to P of X, which is the value at 3, 0, 1, 2, 3. So it's 4. And that is equal to P of 4, which is just 4. So P of X stays at 4. So P of 3. Okay, there you go. So now X is 4. So now we're going to go ahead and check in our while loop. While 4 is not equal to 4, return 4. Very good. So we return 4, and we go back into the for loop here now that we've returned. So far we only have A, which is this. This is A. Now we need to execute it at B. And what was our B? It was 4. So now to the next iteration of B, we're going to say while P of X is not equal to X, which is the same as saying while 4 is not equal to 4, but they are equal, so we just return 4, because right here it's still 4. So now we're going to check. Remember, 3, return 4. So A is now 4. B is now 4. And we're going to say, is A equal to B? So are these equal? Is 4 equal to 4? So the answer is yes, and this is our answer. We found the node that was causing the problem. So answer found. So we're going to go back and see, okay, so we were dealing with 1 and 4. So that's going to be our problem causing edge. 1, 4 is the answer. And hopefully that makes sense to you. We don't even have to check 1 and 5. We still have one more node to check. We still have to check 1 and 5, but we already found the one causing the problem, so we don't need to check this. And as you can see, the answer is 1 and 4. And that's essentially how you would walk through this problem. Like I said, it's a medium difficulty problem. It's solved in this case by using disjoint set unions. There's other ways that you can use to detect cycles, but this is probably a good way to do so. But again, thank you. I hope you understood everything. If you didn't, then feel free to ask any questions. I'll be more than happy to help.